a heads up about where we are in terms of the rest of the year of 2018. So we have spent quite a while, almost an entire month, on energy work, and we're gonna talk about work and power today. So just a heads up, I have adjusted this from yesterday or from even earlier this morning. Today we're gonna spend some time on work and power. Tomorrow we're gonna do a quick lab and the analysis that goes with it. Monday we're gonna talk about more types of energy to kind of pull this all together. We're going to spend some quality time with bar charts to make sure we really get them. I introduced them to you a few days ago, but we're going to dig in now that we really understand them. We're going to review Wednesday. My intention is to test on Thursday of next week. Friday is the last day of school for 2018. So I want to make sure we have a little bit of wiggle room just in case somebody happens to be gone on Thursday. If you know that you will be gone on Thursday and Friday of next week, you need to talk to me before then, please. Not right this moment, but at some time, in the next, 24 hours or something like that, just so that we can adjust. I don't want you to have to worry about that over winter break. That sounds like a really bad choice. So I would like everybody, I'd also like to be able to, grade the tests and things like that over winter break. That sounds like a good time to me. I mean, if you get them all done, then maybe I'll even give them back to you on Friday. We'll see. What?
So there's a math final on Friday or on Thursday next week. So
Okay.
we think the week we take it Friday.
Let's see where we're at.
No.
I have a math final.
Okay.
That's your individually.
Listen, yes. So here's the thing. If you have a specific situation, like what Isaac is talking about, then you and I can talk, okay? I'm flexible, but yes. So yes, we'll figure it out.
Friday then
What's that?
for this class.
For sure we will. Yes, we will do things until May 10th, right? And then we'll do some stuff after that too. So yes, absolutely, we'll do something. But if you have a situation like that, then talk to me individually. But yes, Isaac, we can certainly take care of that so that you're not stressing out. But again, if you know that you're going to be gone because you're doing something besides being in school on that Thursday and Friday, let me know so we can get that taken care of. All right, your notes are out, my friends. Here we go. Here's the situation. This is the beginning of our slow walk through the rest of the period today. Woo, it's going to be fast. I gotta go. All right, in a closed system, what can you tell me is conserved? Energy is conserved. Oh yeah, momentum also too, right? Okay. I disagree. We'll talk about that later. All right. In a closed system, energy is conserved. That's all well and good. That's what we've been spending the last week on. Shh. But we talked about this earlier this week. What is a closed system?
Only two things are inside of it, two objects.
We could have a million. We could talk about the universe as being a closed system, right? Absolutely. Cosmologists absolutely talk about the universe as being a closed system. What does it mean to be a closed system, though? What's the key?
No outside forces are acting.
Right. Yes. As long as you keep all those funny outside forces from acting, then you can always say that energy is conserved. So that's all well and good. And like I said, we've been spending some quality time with that. But today we're going to bring in those outside forces. Okay? So the question is, what if an outside force exists? What if an outside force acts? What's it going to do?
Change things.
It's going to change things. For example, if there's a net force acting on an object, what happens to that object? Think back. It accelerates, right? To accelerate means to change its velocity. And remembering that kinetic energy is 1/2 mv squared, if we have an outside force acting, that means it accelerates, it changes its velocity. What does that mean that happens to its kinetic energy? It also changes, right? Easy peasy, we got that. So you can say that we also have a change in kinetic energy. Okay? So sometimes we talk about that. That's all well and good. Sometimes that force, like sometimes we don't look at, like the process of doing it, but we look at the effect of that force. Let me give you an example. Let's say that I have, no, we're not going to, we'll just the frog right now. Let's say that I have the frog right here, and he's just sitting here and everything's well and good. What kind of energy would you say that he has? Potential. We're going to say no kinetic because he's not really moving, right? People might argue that all the molecules inside of him are moving, but we're not going there right now. We're just going to say, because those are all like inside internal forces, we've got just gravitational potential energy, right? I'm going to externally apply a force to him. Whoa! And now here he is. An external force has been applied to him. Tell me, did I increase his kinetic energy?
No.
Oh, his kinetic energy is the same as it was down here, right? But what did I do? I did increase his potential energy. So sometimes it's an increase in kinetic energy. Sometimes we can look at it and say that a force can cause, how do I say this? System's position to be changed. And remember we said that kinetic energy is the energy of motion and potential energy is the energy related to its position. So if the position changes, sometimes, not always, and we'll get into that little idiosyncrasy in just a minute, but sometimes, for example, sometimes a force can cause a change in height. And if we have a change in height, that means that we have a change in gravitational potential energy. Okay? Anytime that a force acts over a distance, we can say that there's a change to an object's total energy, okay? When an outside force acts, I can't write today. Seriously? Come on, team. There we go. Acts, what did I say? Over a distance. It changes a system's energy. This is kind of like the opposite part to the conservation of energy, right? This is the opposite situation. What do we call that change in energy? We call it, does anybody know? We've just mentioned the word a couple times out there. Starts with a W. We are doing work. Okay. Work is done on a system. The simplest definition for work, this is going to blow you away because, friends, this is a theorem. In fact, this is one of the most fundamental theorems in all of physics. Work is equal to change in energy. Pretty darn simple, right? Kate's like, got it. I got that. Woo, it's good. Work is equal to the change in energy. Okay, this is known as the work energy theorem. That is even simpler than the impulse momentum theorem, right? Like, so simple. Okay, what's up?
I don't understand. What is work?
What is work? It is a force that's applied over a distance.
Force.
Yep. So when I have my frog and he's sitting right here, and then I apply a force,
That's the word.
hot diggity, right? Because I'm adding energy to the system.
So work is a force done over distance.
Yep. And we'll talk about what that looks like in just a second. Yeah.
So like kind of, I guess if the engines were,
Sorry, airplane, is that what you said? Yeah, go ahead.
I don't know, like if the engines were applying force kind of to the plane to get it to move, would you say just to
For sure I would, right? And it's starting off, I'm imagining you have an airplane that's starting off like sitting on the runway, so it's got no kinetic energy, right? And then as it goes, it's going to increase both in potential and in kinetic, won't it? Yeah, absolutely. So good call. Absolutely. Okay. How are we doing? We okay so far? Yeah. I mentioned that we were going to do some bar charts. We're going to do one real quick right now. So here's a really quick bar chart to take a look at. Last time that we did these bar charts, I just told you about the energy in the people that write these, instead of writing just K, they write KE. But we'll just take a look at this. So we're going to write this down. You don't have to write down all these little lines, but you might want to just draw this one and this one and this one, just like a little T. So like if I was drawing this on my notes, I'd probably just do like that one. Here, I'll highlight that. And like, and then I'd label this kinetic energy initial. And then, oh my gosh, I'm going to do work. And then I've got my final kinetic energy. So the situation says that the velocity of a tugboat increases from 2 meters per second to 4 meters per second, moving in the same direction. We okay so far? Yep. The force is applied for 20 seconds. Okay? Complete the work and kinetic energy bar chart for this process. The bar height should be in correct proportion. So we're just going to kind of get a sense of what's going on here. How might I approach that question? Is work being done? How do you know work's being done? That's the first question. Because the kinetic energy is increased, right? So there's a change in kinetic energy. So that means that we know that there was work done. Right now I've got 2 bars of kinetic energy. We're increasing from 2 meters per second to 4 meters per second. How much is that increasing the kinetic energy?
4.
Is it doubling the kinetic energy?
It's like
4.
It's foring it, right? It's quadrupling it. Does that make sense? Do you guys need me to go through that? Let me just remind you, friendly reminder that kinetic energy is 1/2 mv squared. So if you've got a v of 2 for the first one, and you've got, that's going to be 1/2 m times 4. K equals 1/2 m times 4. If you've got a v of 4, now you've got K is equal to 1/2 m times 16. I wrote that really small and down at the bottom, but does that kind of make sense? So I've got 1/2 m times 4, I've got 1/2 m times 16. So we're quadrupling the amount of kinetic energy, even though we only doubled the velocity. So then, next question, if I've got 2 bars here of kinetic energy to start, how much do I have at the end? 8. 8, right? Yeah, because we quadrupled it. So let's go ahead and do that. 1, 2, 3, 4, 5, 6, 7, 8. It's like this much. I hope I counted that right. So we go from 2 bars to 8 bars. And then, friends, this one may blow your mind. Perhaps not. If I start out with 2 bars of energy and I end up with 8 bars of energy, how many bars did I have to add in the form of work? So exciting, right? It's so exciting. And I remember when I first showed you these, I'm like, I kind of thought these were lame. But I will tell you that as you process this, as opposed to me just asking you how much work was done, this gives you a very easy way to figure out exactly how much work was done. You told me 6, right? That was the answer. 1, 2, 3, 4, 5, 6. So something like this. So that's how much work is done. And now I can see that the kinetic energy plus the work that I did gives me that total energy of 8. Okay. More of this to come. I'm going to bounce back to my work, but to my definition of work. I know I had to fit it in there somewhere. It worked out okay. All right. So Henry wanted to know what work was, and I kind of glossed over it there at the beginning, but I'm glad that he asked. Work done on a system is the amount of energy change. That's one way to define it. The other way to define it is literally, it's a force that acts over a distance. Okay? There's a little caveat to that, and we'll get there in a minute. But, bless you. But the piece of it that's really important is that there's a force acting, an outside force, because it's not a closed system anymore, and it's acting over a distance. Okay? So we can think about that a few different ways. We can think about that if we have the frog, and if my system is only the frog. Okay? There's no earth. The system is only the frog. How much kinetic energy does it have right now? 0, right? And I can't have potential energy if I don't have something to be pulling on it. So there's no gravitational potential energy, so 0. 0 energy. And then I let it go, and as it falls, what happens to its kinetic energy?
It increases.
It goes up, 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 up. Why? Because there's a force, the force of gravity, right? That's an outside force now, a force acting over a distance. Is that okay? You look a little perplexed. Go.
I don't know how to phrase it, but it's just like, just because the kinetic energy is increasing the work, that means there's work to be done.
Yeah. Because if you have any change in energy, there has to be work done.
Even a change in potential energy, there's also work being done.
For example, yes. You will think of this now forever. You're welcome. Okay. I bought this when I was student teaching because the book that we were using gave this big description about how when you lifted a cheeseburger, you were doing 1 joule of work, and it just like it's sweet and it's hilarious. So anyway, I want you to imagine this: that you happen to be sitting at a table, I don't know, at a restaurant or at your house, and a cheeseburger is in front of you, and you're like, man, I'm super hungry, right? So what do?
Lift it to your face.
You're gonna lift it to your face. Now, as you lift it to your face, if the cheeseburger is all we're talking about in the earth, right, I'm going to apply an outside force. You with me there? Which way is my force going? Up, right? I'm going to apply a force over a distance, and in doing so, I am increasing the amount of energy that cheeseburger has. Are you with me there? I'm increasing the potential energy, so I'm doing work, right? So now you're doing work while you're eating your cheeseburger. Absolutely. Is that making sense? Is that okay? Yeah, practical. Now, quick question for you. Let's say that so you've moved on from just eating cheeseburgers. Your parents are like, you got to get a job. So you decide that you're going to be a member of the wait staff at some fine cheeseburger selling establishment. And so you have the opportunity to have this big tray full of cheeseburgers. I've just got one. And I'm going to walk it like this. Am I applying a force to the cheeseburger right now?
No.
Yes.
I have to be, right? Because if I was not, where's the cheeseburger going to go?
Down.
It's going to go down, right? It's going to go down. But, so yeah. I am totally applying a force to the cheeseburger. Am I doing work on the cheeseburger, however?
No.
If I'm moving at a constant speed, are you with me there? Moving at a constant speed, so I'm applying a force. Is there a distance involved?
Not for the cheeseburger.
Yeah.
I mean, you're not moving.
Now you're moving.
That's the trick, right? Am I increasing its potential energy?
No.
No. If I'm moving at a constant speed, am I increasing its kinetic energy? No. So am I doing any work on the cheeseburger? No. No work is being done, even though I'm applying a force over a distance. So what's the trick? What's the thing that has to be true about the force and the distance?
Vertical distance.
It has to be like this, right? Now I have a question. Let me ask it this way. What if, let's say you go to this cheeseburger restaurant, and instead of having like everybody gets their own cheeseburger, there's just a big platter of cheeseburgers in front of you. Okay? Big, like on the big lazy, so you're like, so the cheeseburger is there. You need to get the cheeseburger to you so you can consume it. Yeah? Like, that's a thing. So I need to apply a force over a distance to get the cheeseburger. That's a horizontal force. Am I doing work on the cheeseburger?
Yes.
Yeah, I totally am. I am bringing it closer to me, right? Even if there's friction, right, I am still doing work on the cheeseburger. So I'm applying a force over a distance like this, and yes, absolutely I'm doing work.
Wait, what energy would change though when you're moving it like that?
Well, if there were no friction, then the cheeseburger would accelerate, right?
Yeah.
So the friction is also doing work on the cheeseburger. So the net work on the cheeseburger is 0, but I am doing work because I'm applying a force over a distance on the cheeseburger. Are you with me there?
No.
I'll say it again tomorrow. I'm keeping an eye on the clock because I need to go through one more thing. So for right now, Henry, I want you to take a deep breath and go with me, and then we'll come back to this again tomorrow. So the key here, friends, the thing that I'm trying to get at, and maybe I'm not doing quite a perfect job yet, is that the force and the distance must be parallel. In your textbook and in many physics textbooks, they will say that work is equal to force times distance times the cosine of theta, the angle between the force and the distance. This always makes me nervous, probably because I had some bad experience at one point where I picked the wrong theta. You with me there? Because if you break the angle up the wrong way, then you get the wrong theta. The thing you need to know is that the force and the distance have to be parallel. And it's only the component that's parallel. So for example, if I've got a box, a mystery box or something, right, and there's a string that's acting like this, it's like we've seen this problem before, right? And I'm applying a force in this direction. Whoops, come on. Okay, but the box is just sliding along the floor. And so the displacement is in this direction. Are we doing okay? You with me there? Okay. The only part of the force we care about is the horizontal part. Okay. So in that case, it would be just this part here. If you call that theta, then indeed it is the cosine. But again, if you pick the wrong theta, then so I don't like that because it makes me feel a little bit uneasy, nervous. So I just like to say it's the parallel part. So here, it's the force acting like this, and the distance is like this, and hot diggity, those are parallel, so you're okay. Okay? We okay so far? Ish. I've got one more thing, and I've got 2 more minutes, so it's perfect. All right. Not only did I want to define work today, and we'll do some more problems with this. Your homework is over this. You'll get some more practice. The other thing that I wanted to define is power. And power is very simple to come up with once you understand work. Okay? Power is literally the rate at which energy is added or removed. Oops, come on, eraser. Or changed. Bless you. So if we take that for what it says, rate means that we're going to be involving what? Time. Did you say time? Change in time, yeah. The rate at which energy is added, removed, or changed, that's really work. Power, the equation for it is work divided by time. My calculus friends love that, right? It's a nice little derivative to do. We'll do that another day. But anyway, power is marked with a P. Work is marked with a W. Time is marked with a T. The reason I'm saying that is because it gets a little tricky when you start looking at the units. We haven't mentioned this yet, but what's the unit of work? It's going to be in joules, right? It's going to be in joules. Time is going to be measured in seconds, and power is measured in watts. This is why it's weird, because watts is marked with a W. So you've got P is equal to WT, but P, the units are W. Are you with me there? So just be careful. It's not too hard, but you just have to be careful with it, okay? I think I made it with 6 seconds to spare. What? I know, it's awesome. We'll come down, we'll do more of this tomorrow. Have a great day, you guys. Woo! Yeah, hold on just a sec.